Well, good job. I hope everyone had a good weekend. Are there any questions we have to discuss before we dive into the lectures? Anything about the homeworks or quizzes? We're good? Okay, so hopefully everyone is close to completing the homework, and we will release the next homework, which will be about the system boot. You will have to boot into the whole world, like I did in one of my introductory lectures, right? So that will be your homework assignment. So, okay, let's quickly then finish address translation and finish discussing the page tables, and then start talking about the system boot. So, just a recollection, right? So we first started looking at a very primitive hardware address translation mechanism, which is called segmentation. And then we said, okay, it's not flexible enough. It was good for the early systems, which were relatively simple, and the hardware was expensive. But as we moved forward with more complicated CPUs, which allowed us to put more transistors, like implementing more sophisticated hardware translation mechanism was not a problem, right? And so CPU designers said, okay, we're going to build these page tables, which essentially represent memory as a collection of chunks of a size of a page. And I was saying that page size can be different, but on x86, it's 4096 bytes, so 4 kilobytes. And this data structure, the page table, which is essentially a radix tree, translates each page individually, right? And so let's quickly discuss the benefits of this approach compared to segmentation. Right, and like first of all, we can translate, we can achieve the flexibility with an address space, right? So if we need to grow the address space by just a single page, maybe you do another memory allocation, and you need more physical memory, which backs up your virtual address space. You just add the one element in this radix tree, essentially, ensuring the translation of a page, right? And we were also talking about the benefits of page tables compared to something like arrays, right? So, and remember, I was saying that that the page table essentially occupies less space in most cases. So remember, we said that if we want to translate the entire address space with an array, we need 4 million pages, which means we need 4 million entries in the array, which means we need roughly 4 millions multiplied by 4 bytes, so 4 megabytes, right? So let's eyeball the size of the page table data structure. So what is the minimal page table? I mean, we talked about it last time, and I was saying that it's kind of like a Google level interview question. And I said that really, like, if you're clever enough, you can loop the page table like that and essentially use just one page. It's very exotic. So I believe I've seen it in practice once, but in some early boot stage code, but no one really does it because it's so exotic that you probably don't really need it, right? But in most cases, like imagine you have a tiny process like cat, right? So cat will have maybe one page of text, maybe one page of data. Like if you really want to save space, you can link text and data into one page as long as it runs, right? You can even put the stack on the same page. But let's imagine we're not as greedy and we say, look, we'll put another page for the stack, right? So literally your address space to start running is just 3 pages, which means that you need to translate 3 pages, right? This is your virtual address space. If I ask you a question, what is the size of the page table for this example, when you only have to translate 3 pages? Pages you will need to allocate for this radix tree. That will be in a quiz today, so just to wake you up after the break. Anyone? Yeah, okay. Try guess. Yeah, 2 levels. So how many pages?
So 2 pages, 1 page.
I agree. So there will be a root of a page table, which is also has a name, which is called page table directory. And then it will have a pointer to at least one page of the second level, which is just called page table for whatever reason. So hardware register CR3 points to the root points to the leaf, right? So 2 pages. That's one case, right? It's a case when all these pages live in a consecutive region of 4 megabytes of virtual address space, right? Because one of these leaves, it has 1024 entries, right? So one entry controls 4 kilobytes. So 1000 by 4 kilobytes is 4 megabytes. So one leaf can translate consecutive addresses of 4 megabytes, right? So that's okay, you got the point. So if suddenly, I just wanted to go back. If suddenly your address space is such that these 2 pages live in first 4 megabytes, and for whatever reason you decided to allocate this stack in the next 4 megabytes, right? Then what's the shape and the size of the page table? You're looking at me, yeah.
It's got the one root page, and then it's got 2 leaf pages.
Exactly, one root and 2 leaves, right? And if these two 4 megabytes regions are consecutive, those entries in the page table will also be consecutive, right? So because that's how the translation mechanism works. Remember, the main motivation, we split the address space into chunks and said, okay, if we're using this chunk, there will be a leaf for translating this chunk, like an array, right? And if you don't use the chunk, then the pointer is empty, right? But if the chunks are consecutive, then the entries will be consecutive as well. Is that clear? Well, agree. Okay, so 2 leaves, and in the max case, obviously, since we have 3 different pages, and if we split them in like 4 megabyte regions, you might end up with a 3rd leaf as well, right? So then you're like, maybe you're unlucky, maybe you do it on purpose, maybe you use some address space layout randomization and you just put those pages in random places, right? And most likely you will use a page table which has 1 root and 3 leaves, right? So the total size of this page table will be 4 kilobyte multiplied by 4, right? Agree? Okay, so that's pretty typical, and it's nice compared to the array, which immediately requires you to allocate 4 megabytes upfront, right? But what is the size of the page table which translates the entire address space? Like essentially imagine every address in the address space is translated. Then what will be the size of the page table data structure?
So there are 1024 at the leaf, right?
Correct. So you will have 1024 of these, right, leaves, and 1 at the root. So the total size will be 1024 multiplied by 496 bytes, 1 page, right? Plus 496. Like if you round it up a little bit, it's 4 megabytes plus 4 kilobytes. So it's even larger than the size of the array because there is no magic. If you say, I want to translate the whole address space, you will have to translate every region. So you will have every leaf and plus 1 root, right? So, but in most cases, this is not the case because, I mean, you can argue that today this is the case for many programs because a lot of programs these days, even web browsers, easily use more than 4 gigabytes of the address space easily, right? So like Firefox uses probably more. But back in the days, the address space was sparse. Today, we switched to a 64-bit address space, and I will explain how it works in a second. And that space is also, in most cases, sparse, right? So your page table is relatively like efficient just because you don't translate all the addresses, right? Okay, let me stop here. So, any questions about it? Good. All right. Well, my quizzes are designed to help you to understand the page table translation. So, unless you took it, so get ready. It will be there today or tonight on the quiz, right? So, which is due today. Okay, so we talked about page tables, but remember, we want this property that the 2 programs cannot access memory of each other. So the way we solve it with page tables, right, is kind of similar to how we did it with segmentation. So each process has its own page table, and the operating system will switch between the page table when it will be switching between processes, right? So remember, I was saying that we will save the state of a running process, load the state of a next process, and part of the saving and restoring will be a switch from one page table to a different page table. And the operating system is free to control the page tables, right? Because the user applications cannot control it, right? So essentially here we have two processes, one green and one pink, and the operating system is setting up the page table translation. So it uses two different page tables, one for the green, one for the pink. And essentially pages of the green process typically do not overlap with pages of the pink process, right? So just because the translation works this way. So essentially if green accesses this address, it goes somewhere here. If pink accesses the same address, it will just go to a different physical page table, right? So this is your physical memory, right? And everything what is above, we typically call virtual, although Intel has a specific term for that. Remember, it's called linear. But you can use virtual as a term. Everyone will understand you, right? So essentially, the addresses which are in your registers, if you essentially do something like move EAX from the address pointed by EDX. So this EDX value is just treated as a number, which first goes through the segmentation. Oops, sorry. And it's impossible to disable segmentation on Intel without disabling paging, right? And then whatever the exit from this translation is, again, the number goes into the page tables, and eventually it becomes, again, a number, and this is the number, which is a physical address, which we place here. So physical address. And this goes on a memory bus and essentially tells, okay, yes, we will access this location, right, in memory. Is that clear? Okay, so remember we were talking about position-independent code and sharing libraries, right, between processes, right? Operating system does this with page tables. Essentially, if you say, look, my libc is sitting, for example, here, the text section of the libc library, right? Then those pages in two processes, and okay, this is a bad example because let's say, because this implies that this uses the same virtual address. So let's say libc is loaded here, right, in this other process, right? Because it's position-independent code, we can load it in any address, right? So there will be, remember, there will be a POT table for functions and GOT table here, GOT here, and maybe GOT here, right? And then the operating system says, okay, look, since I loaded already libc once, maybe in a pink process, when it loads the libc into the green process, the page table is configured to make sure that the text section of the libc points to the same physical pages, right? They can be in a different address in the address space, but this is how the sharing is achieved, right? And since page table has enough flags to say that this mapping is read-only and this is read-only, so both programs can execute the page, right, but cannot write into it. So this is how we achieve isolation between them, right? Is that clear? Okay, that's why I was again trying to explain position-independent code, because this is how it works in real life, right? So this is how the sharing is implemented in commodity operating systems like Linux, Windows, and Mac OS, right? Okay, so again, back to this benefits, just to recap them. Page tables allow you easily emulate a larger virtual address space on top of a physical memory, right? In my rudimentary example, I had only 12 physical pages, and I still can emulate the whole 4 GB address space by essentially controlling the flags in the page table, saying that the page is not present when the program tries to access this page. Hardware generates a page fault. Operating system reacts to this page fault, saying, okay, yeah, I know that you should have a page here, but I temporarily took it to disk, for example. Or in my data center example, maybe it's on another server right now. And you just move the page back, map it into one of available 3 pages, and restart the program. Not restart from the beginning, but let it run again. And since you already fix the page table, this time this move instruction will succeed, and then nothing happens. And it's transferring to the program besides the measurable time, because you can measure how long it suddenly took you to access this element of the array. And suddenly all elements of the array take maybe 200 cycles, and a page fault takes, I don't know, depending on where you're running, from several millions of cycles to several thousands of cycles. Like, depends on how well you optimize it, right? And this was a big deal, as I said, back in the days when the memory was scarce. Today, memory is less expensive, but again, we have those remote memories in the data center. So we kind of made a cycle again and facing the same problem with slightly different set of constraints, like faster. It used to be go to disk to read the page. Now it's go over the network, just because networks are faster than disks these days, right? Okay, so this is the sharing of my libc one more time. And it just doesn't have to be always just libc. Remember, if you really want to communicate between the program very, very fast, so imagine this program is some part of your like graphical user interface, and really this program like writes into some magical memory here from which it gets picked up by the graphic adapter, like VGA, for example, or whatever, HDMA goes to disk. So essentially, this is the frame buffer. And this program uses a window library, which, for example, says, okay, my window looks like some letters here, hello. And this program is a compositor, which puts this hello maybe under some other windows, right? So maybe hello sits here. So this one will essentially compose the final frame buffer, but this is just says, okay, this is my window, this is my hello. To make sure that communication is efficient between these two programs, it makes sense to create a region of a shared memory. And we once used this in the homework, I used this Mmap system call. So it's a typical system call which allows you to mmap a file or a region of memory without a file backing it in multiple letter spaces. And essentially, if one program writes something like H, for example, here, this H, since it goes into this physical memory, gets immediately visible here, right? And so this goes with the speed of DRAM. So it's not a pipe, which is relatively slow. You can only write 512 bytes in an x86 pipe, maybe 64 kilobytes in the Linux pipe. Then you have to invoke a system call, kind of you do a read call, and then on the other hand, on the other side of the pipe, you do a, like on one side of the pipe, you do a write call, on another side of the pipe, you do a read call. Here, you just write into memory. So it's less than one cycles, especially if you write multiple bytes, right? And it immediately becomes visible here. So this guy, maybe it's running on different CPU, for example, immediately picks it up and can do something with it. So it's a way to implement efficient inter-process communication. Is that clear? Is it clear that, like, if you write into one memory, since it's the same physical memory, this is immediately reflected in the address space of a different process, right? And I will explain how it works when you're running on two different cores, on two different CPUs, like it's called cache coherence. So we'll get to this a little bit later in this class. Any questions? Okay. So, and just to recap, this is the full translation pipeline. By the way, this is a picture from a book. So it's again kind of time to start reading the book, because I do have a couple of assigned readings from the x86 books. So remember, CPU starts with something what is called the logical address. It uses offset. And where is this offset stored? Where is it? Do you remember? Last bits of the address, not quite. Remember, this is the page table, this is segmentation. So where is the offset? In a register, right? Exactly. So if you have something like move again into EAX from memory pointed by EBX, offset is this number, which is stored inside the EBX register, right? So this is an offset within a segment. Remember, this is still segmentation. And where is the selector? In a segment register, right? There is a set of other registers, CS, DS, we'll see in an FS, SS, doesn't matter. So this is essentially kind of a number which points to the table, which is called global descriptor table, and essentially chooses an entry, and this entry will have a base and a limit for the segment, right? And this base is added to this EBX register, right? So roughly here, you will have something like EBX plus base, right? Right? And Intel calls this a linear address because it's not two components, but just one. So now it's linear. They came up with this term. Typically, people just call it virtual. And this number becomes an entry to the page table translation, right? And so the page table translation then goes to the page tables, right? And you get the physical address, and this one goes to DRAM, right? Clear? So it's a little bit convoluted, but again, I wanted to make sure that we understand it. This is how it runs on Intel. This is how you will have to boot in your next homework assignment. So watch out. In many cases, people just, in modern days, since no one wants to deal with segmentation, the base is often 0, which means that this translation is almost like invisible, right? It doesn't change your address. So your number stays the same just because you're always adding 0, right? It's not always the case, and I will explain when it's not the case. Just a hint, it's used for implementing something what is called thread local variables, right? Again, we'll go through an example, right? But again, this is the final kind of picture. And just again, to make sure that everyone is like sick of it, right? For real, just one more walk through the Intel diagram. So you start with the logical address, right? You will have two components, like a segment selector and an offset. Offset is in the register, like we just discussed. So selector chooses an entry in a global descriptor table, right? This entry will have a base and limit, and it's added to the offset. We'll get a linear address. This is just an address space, right? So roughly speaking, it's kind of like a virtual thing. It doesn't exist in physical world. It's just like you say that's just space of numbers. But you take this number, and essentially what you do is that you say, I will split it into 3 parts, right? And we'll use it for translation in this radix tree. So and then I will get the physical address, right? So these 3 parts, the directory itself will choose an entry in the page directory, right? Let's remember, we split the address space in 4 megabyte chunks and say if this chunk is being translated, this is the number of this chunk, right? So this defines 4 megabyte chunks. And then within the 4 megabyte chunk, you will use this 10 bits. So this is 10 bits because 10 bits allow you to represent 1024 numbers, right? These 10 bits will choose an entry within a 4 megabyte chunk, and this offset will finally choose an address within a page, right? So, and this offset is 12 bits because it allows you to represent 4096 bytes, right, within the page, because each page is 4096 bytes. Okay, so we got it. So, as I was saying, originally page tables were just fine. They were solving all the problems in the world, and everything was super elegant, and just one page size, 4 kilobytes. It turns out that this translation through a page table has a non-negligible overhead for some workloads. Why is that? Because literally you say, look, imagine you reading, let me erase here everything. Imagine you're reading a giant hash table, or just for the simplicity of the deal, it's just an array. But your access pattern is random, meaning defined by some input, and you don't know upfront the sequence of the elements which you're going to access, right? Imagine this as the entire 4 gigabytes minus some delta to run the kernel and the code, right? But you say like really large data set. Let's assume a genome or something, right? Every time you say, look, I will access a memory address, right? You will expect to pay the price of how many cycles? Vector cycles. I keep mentioning cycles, so you should have a good feeling of how long it takes to access memory. That's correct. So what your classmate is saying that instead of just one memory access, which takes how many cycles? I just wanted to hear the number, just so we all remember. 250 cycles. It varies, and I will talk a little bit, but one memory access through a memory controller takes 250 cycles, let's assume. But what your classmate, you're saying my page tables, my access should have a price of 250 cycles. But in practice, You first have to access this element in memory and this element in memory, right? And where are those page tables? They are somewhere here. They are also sitting somewhere here in memory, right? The root and the leaf, right? Because they have to be in physical memory, which means that you also doing this memory access, that's access number 2. And let's even like order them. This is access number 1, this is access number 2. And only after that you access the actual element in the array. And this will be access number 3, right? So let's eyeball how long each of these accesses will take. So who can tell me how long it will take to do the access number 1? That's okay as a first attempt answer, but think a little harder. Remember the caches. So people, I mean, at this point, everyone was in the computer organization class. I teach one, Rajiv teaches an excellent class. Who remembers caches? It's like the core of your computer. Your computer doesn't run without caches, or every instruction takes 250 cycles. Okay, not every fifth instruction is a memory access in realistic code. So it's like 4 instructions which take 1 cycle, and then instruction which takes 250 cycles. Clearly not a good idea. That's why we use caches. So how do caches work in this example?
The page directory would be in the cache because it's always being used.
Exactly. So most likely, okay, what are the sizes of the caches? Who will tell me? I'll give you a hint. There is a hierarchy of caches, L1, L2, and L3. They get larger but slower. So what's the size of L1 on Intel? What? Kilobyte, but how many kilobytes? 4. Anyone else? Computer organization, come on. Failed? Everyone failed? That's your chance to recap and go talk to Rajiv and say, look, I finally got it. I got it why we did caches, right? So anyone guess? Okay, I'll teach you how to learn it. Okay, but it's 32 kilobytes. So clearly, if one page is 4 kilobytes, so there is enough space to have it here, right? Access to the first level cache is how many cycles? No? Yes? Again, computer organization? 2 to 3 cycles. Remember, Agner Folk, I even showed you the tables. And typically, read and write to memory takes 2 to 3 cycles because it hits first level cache, right? Okay, cool. Now the question is, what happens to the second write? To the second access, which accesses the leaf of a page table?
I guess if you recently accessed that same page table, that it would also be in like the first or second level cache versus your first time in.
Correct. Your intuition is correct, but let's think a little bit harder. And this is why I was trying to explain you how much space the full page table might occupy. Remember, I said that this is the full address space, full 4 gigabytes. We're translating every page. Then what's the size of the second level? We just talked about it a second ago. How many? 4 kilobytes? Man, remember, if we're translating the whole thing, each of them is 4 kilobytes, but we have 1,000 of them, right? So it's equals to 4 megabytes, right? And so if your access pattern is truly random, because it's important what the access pattern is here, right? You're accessing those addresses all over the place. So you say that I will access any of these 4 megabytes realistically. And this becomes a question whether it's cached or not. So clearly it's not in the first level cache because it's 32 kilobytes, right? The second level cache can be large on modern machines. Just a couple of years ago, it was 256 kilobytes on maybe even on my laptop. We can double check a lot next time, just not to waste time today. But on server machines, it can go up to 1 megabyte. And the last level cache can go up to 1 megabyte per core, meaning that if you have a 16 core machine, it will be 16 megabytes, right? So on modern servers, it will fit in the last level cache, right? And the access to the last level cache is roughly 30 cycles, right? And so your second access is 30 cycles, right? So the total time to access is like 3 cycles for the first level cache, plus for the first level for the directory, plus maybe 30 cycles. This number is growing as well for the level 2 of page table, and then truly 250 cycles for the memory access itself, right? So, and it depends. So like, again, if you're unlucky and your last level cache is less than 4 megabytes, then this time immediately goes to 250 cycles as well, right? It's just on modern machines, it's still 250 cycles. But unfortunately, modern machines use larger address spaces. So you will see the same picture coming back. Okay, so the hardware designer said, okay, we clearly see the problem. So the access time can easily double just because he will be doing this translation. So they implemented a special mechanism, which is called translation leukocyte buffer, TLB. And this TLB essentially is a tiny cache on the CPU, which caches virtual to physical translations, right? So for frequently accessed pages, the virtual to physical address will be cached in this TLB. But TLB is also limited capacity, maybe 128 entries, right? So it doesn't help you with this page table, right? And so the solution which they came up with is just saying, okay, if you really have a giant address space, if you're going to use it all, forget about these 2 levels of translations. Like just translate 4 megabyte chunks directly. So your page size, the second page size, which 32-bit version of Intel hardware supports, is 4 megabytes. How does the page table look? It's just one level because you don't need to have the second level of translation. You say, I split the address space into 4 megabyte chunks. I will have a root of the page table, which will contain 1024 translations, and it just will contain immediately the physical address of the chunk, right? And they can be put anywhere in the address space. They can put all together in one chunk, right? If you are so crazy and you have a need for that, right? But this is how it works. And then you have a guarantee that this thing, which is only 4 kilobytes, is always cached in L1, right? So if you're absolutely after extreme optimizations, like hash tables, some workloads which run on thousands of machines, and if you can optimize them even by 10 to 20%, you save a ton of money in millions, right? You do this trick. You essentially say, instead of using 4 kilobyte pages, I will use larger pages. And it's called Superpages, right? So, or larger size, right? So just again, make sure that you understand that this is the option and this is why it's done. Just because you say, I want to eliminate the overheads of translation, right? Any questions?
Typical operating system let you designate pages for your application.
Right. So modern Linux machines, but we'll talk a little bit in a second. On 64-bit addresses, there are 3 page sizes: 4 kilobytes, 2 megabytes, and 1 gigabyte. So the operating system transparently allocates 2 megabyte pages for you to say, if I see that you allocate a bunch of consecutive addresses, I will just allocate you a 2 megabyte page because I know that it will save you some time. So you don't even notice. But if you want to use a super page, like a 1 gigabyte page, then you have a slightly different interface and you say, please allocate me those giant pages explicitly. For now, this is the interface. Just because they said, okay, it's so rare, still so rare that we're not going to do it transparently. But you can figure out how, like, essentially run an algorithm which just grabs a bunch of pages and put them in a single super page and reallocates transparently as well. I mean, we use it in practice in my research, just to save those last bits of performance. People who do databases and they have to do joins, right? So essentially very large memory data sets of like different tables, they do this optimizations. Again, genomics people do the same just because they count every cycle. So again, if you're in these areas, just make sure that you understand how it works. Okay, let me quickly, this is like the Intel diagram, just to be more concrete here. Again, you have you have your linear address, but now you say you have since you have to like designate one of those 1024 chunks. You take 10 bits of the address, right? So this is the 10 bits. CR3 points to the root of the page table, control register 3. You choose an entry here. This exactly gives you 18 bits of the address, meaning that everything is aligned at 4 megabyte boundary. That's why it's 14 megabytes. That's why it's 18 bits. And you have the physical address or physical page number of a physical page, right? And this 22 bits is the offset, which chooses one of those 4 million bytes within the 4 megabyte page, right? Okay. Finally, as I was saying, when we switched from the 32-bit to 64-bit address spaces, and the need for that was kind of natural. So essentially, applications started running out of memory. So your web browser suddenly said, okay, I cannot fit into 4 gigabytes of address space. Moreover, some of it was occupied by the operating system itself. So let's say 3 gigabytes. It looks large, but roughly 15 years ago, people said, okay, we're running out. And so the hardware designer said, okay, here we go. We'll switch to 64-bit address. And with this will come a larger address space, right? So this is your linear address. It's a little bit, it says 64 bits, but only 48 bits are used, right? The top bit is 47. Like the other bits will remain unused. So depending on what the hardware, like how you configure it, it either is ignored completely or just triggers an exception if you have some illegal values there. You can, sometimes hardware uses some security flags there in those top bits of the address, right? And okay, so you say, look, I will translate 48 bits of virtual address because they believe that they don't need anymore, right? Into, they said 52 bits of physical addresses. They said, okay, for a while, we'll support 52 bits of physical address. So that's, in theory, we can support up to 64, but this is large enough to get it going for a while, right? And so the translation looks very, very similar, but slightly different, right? So since your page, they said, okay, the page will remain 4,096 bytes, right? But now each entry in this page, instead of 4 bytes, started taking 8 bytes. Just because, remember, we needed 20 bits of address to say, where is this physical address space? But here we need more bits of address, right? And the bits were not fitting, so we need 40 bits now. We're not fitting in 4 bytes. So they said, okay, each entry is 8 bytes now, which means that instead of 1024 entries, there will be only 512 entries, right? But the idea is the same. So it's a radix tree, but now instead of 1024, it's 512. And so you say, instead of 10 bits of address, you take 9 bits of address to choose one of those 512 entries, right? And so you get the entry here from the root of the page table, take 40 bits of address to go to the next level, which is 4 kilobyte aligned. Again, take 9 bits here, choose an entry here, then the next 9 bits, choose an entry here, and the next 9 bits, choose an entry here. And finally, you have a physical page, and the offset within the page didn't change because the page size didn't change, right? And it's still 12 bits, right? So, but now you have 4 levels of translation. And if I come back to this story about the access to the large array in memory, it was a random access pattern, you can say that this one is 4 kilobytes, right? And it's clearly cached. This one can be at the very max 4 megabytes, and it also can be cached in my caches. But now you have like 512 of those, so it's 4 megabytes multiplied by 512, right? Because you have 512 entries. And here you say, look, this is where I kind of ran out of memory in my caches whatsoever. So most likely this is like a miss into the last level cache. So this will have 200 cycles. This will have 200 cycles. And then the final access will have 200 cycles, right? If you're really like on a large address space, like it did giant terabytes, then those will be your misses, right? So roughly speaking, you can, instead of paying a price of 250 cycles, I was using number 200, so let's use 200. You will multiply it by 3, right? So that's a huge hit. And that's why in the 64-bit modes, the super pages are even more important, right? Just because you say, look, if I'm really anticipating this this scenario, I will just collapse my two last levels and we'll be running 1 GB pages, right? That's still a practical trick in today, right? So you have to be aware of it. Okay, good. Any questions? Okay, so done with translation. So the quiz will test you on the understanding of segmentation and paging. It's very important. Your homework will ask you to construct a page table which maps some region of virtual memory. You like probably next week or 1.5 weeks, right? Not released yet, but will be released tomorrow, for example. So just make sure you understand paging well, right? Okay, now ready to switch to our wonderful lecture about the system boot, which is finally, after all this prep work, we are finally ready to start looking at the operating system code. So at some point, this should be my lecture number 2 after introduction. Or if introduction is 0, that should be my lecture number 1. I spent a fair amount of time to kind of prep you, to make sure that we are on the same page. We can talk the same language. Cycles, address translation, what's inside the ELF file, right? We spent a couple of months doing this. So you can argue that this is worth it or this is not worth it. I mean, it's just kind of impossible to teach my version of this class without it, right? So it's needed. But finally, we're ready to start booting. Okay, boot is kind of excited, right? So what do you think what happens after we power on the machine? Who can tell me? How do we even get to the operating system? First line of the operating system kernel.
You put the first line at the very start of memory, just have that be by hardware first thing then?
Not a bad idea, but memory is volatile. You turn off the power, remember it's capacitors, so you always have to, it's actually, what is it? Dynamic access, what is it? SRAM, static, dynamic, right? Meaning that you have to read the cache line and write it back constantly underneath, just because the capacitor dissipates the power, right? And you have to and if you switch off the power, you're gone. Today we have non-volatile memories, but still everything is designed to be volatile. That's, you know something clearly. So what your classmate is saying that we can designate 512 bytes on disk, like the very first address of the disk, and put there something what is called a bootloader, right? But we still have to get to the bootloader, right? So the question is which line of code and where does it come from executes on the machine?
Start with the BIOS on chip.
We start with the BIOS on chip. So what is this BIOS? BIOS is just a fancy word for basic input-output system, right? So it's the same software which is written by typically by the motherboard manufacturers, written in C and assembly. And this is the first thing which runs the machine, and then it jumps to the boot sector. So, and I managed to say that the memory is volatile. So the question is, where do we save this BIOS? So there is a tiny chip which is non-volatile, which you can flash. This is what you probably heard it. You flash the BIOS or do the BIOS update. So you can. This is the memory which can survive reboots. Essentially, it's persistent, right? So a different technology which allows you to store things. It's read-only. You cannot really easily write it. Or you can only overwrite it once in a while, but you can store your stuff there, right? It's a little bit more complicated than that. Although I'm glad that you know those things like boot sector and a BIOS, right? So the boot sequence is a little bit complicated, and only people who do security research kind of know it today. I know it a little bit, so my understanding is kind of more of a curiosity, but I will still share it with you just so you understand that it's kind of a harder problem than just jumping to the boot sector, right? So the good resource is this document which is called Intel SGX Explained, and SGX is an Intel Security Enclave. We'll talk a little bit about it later, but it's written by a couple of professors from MIT, and they essentially explain how the system boots. And at a high level, it's a sequence of those different software pieces which initialize your platform, like your network cards, your memory, your caches. And there will be a lot of those pieces, like not just a single one. So BIOS is here, bootloader is here. So bootloader is the ones which jumps to the OS. BIOS jumps to the bootloader, right? But there is also microcode and something what Intel calls a management engine. Let me explain what it is. A high-level takeaway from this lecture is that the operating system, despite the fact that the book will teach you that it's the most privileged level of software which runs on your machine, is really not. If you say, I wrote my operating system, I booted it, I own this machine, the answer is no. You might not own this machine. When it matters when you do financial transactions, for example. You run a data center and you don't even know who owns it. Maybe someone is overlooking you. Maybe someone flipping bits, right? And the outcomes of your computations are controlled not by you, but someone who controls the lowest levels of software. So for security researchers, it's important to understand how the platform boots and how to ensure security of the platform, right? So today there is at least 2 layers of software which are running under the operating system kernel. And this is not counting the hypervisor, which is typically running in the data center. There's 2 levels which are given those. If the operating system runs in ring 0, the hypervisor will run in ring -1, user will run in ring 3. So that's just, you understand what these rings are. But imagine like lower, the most privileged, right? The more privileged. So there is a system management mode, which is always running ring -2. This is configured by the BIOS. And there is also Intel management engine, which is also running, which is given a name ring number 3. Okay, let's take a look quickly at what these things are, because it's kind of interesting, right? So if a couple of years you were to buy a motherboard, this is kind of like a better gaming motherboard, right? And you say, like, I will put my CPU here. This is where my CPU socket will go, right? There are other chips on this motherboard, right? And if I provide you a conceptual diagram of this motherboard, right, typically you just think, if it's one core, there's one CPU and one DRAM attached to this CPU with the controller, with the memory controller. This is the thing which takes 250 cycles, which we discussed today, right? And, you know, like we talked about it earlier in a class, if you have a memory and a CPU, the peripheral devices are attached on different buses, right? So if you essentially, if I go back here twice, right? So this is where you will, these are the memory slots where you will put the DRAM. It says here DDR3. And these are the slots where you will put like PCI devices, like your network card, if it's not on chip, right? Your GPU will go, or a graphic card will probably go into this slot. And these are all connected with like buses, which eventually lead to the CPU, right? Just like a high level, no details introduction, right? So those are the buses. There's like another chip which implement this platform control hub, PCH, goes to the controller which controls the disks, goes to the controller which controls the USB. And this is called the PCI bus, like the main bus on like Intel machines or personal computers in general. And this is the network interface, and this is a solid state drive which is attached on a PCI bus, which is much faster than your old SATA bus, just because this is a fast hop versus like you go through this chip and this chip just to get to the disk. So this is, it's not only just the spinning here, like it used to be just the spinning which was killing the deal, but communication over this bus is also quite expensive today, right? But okay, so this is kind of your laptop or a cell phone machine. Although like on my laptop, everything is soldered, cell phone, same soldered. Sometimes some components are integrated here, so the network card can show up on this die as well. And if you say, okay, I'm going to the data center, this is a picture from Marine Engineering Building, Mmap data center from a couple of years ago, right? So racks of machines, and this is one of the blades which sits here, right? This is like a higher end blade from Dell, like R830. So then your diagram on this machine will look something like that, right? So you will have, look, I have multiple CPUs on the motherboard, right? There will be 4. Each CPU will have its own cores, maybe like, let's say 16 cores each, right? 16 here, 16 here, 16 here, and 16 here. Each of them will have local memories. And the latency to this one is 200 cycles, but you can quickly guess that if you're going to access this memory, there is some additional cycles here and here, right? We'll talk about it, but roughly speaking, it's 150 cycles multiplied by 2 each hop, right, between the cores. So memories can be also local and remote, and it's important to optimize for that as well. And your peripheral devices will also be attached to PCI bus locally to each CPU and remotely, right? So it's again different latency for them, right? So okay, cool. So this is why I was saying, okay, this is the general picture. So you might have multiple sockets, right, which will be connected with these cross-socket links, right? And they sometimes even like sit on 2 different like physical system boards and are connected like physically between them. So this Dell has two floors, like the main floor and the upper floor, and then like 2 sockets sit here and 2 on the main floor, right? Just again, but these things kind of stay the same. This is where your BIOS and everything else sits. So let me explain how it works, right? So there is this chip which is called PCH, Platform Controller Hub, right? So it's a microcontroller, right? So it's a different CPU. So this is like your Intel x86 core. This can be some other core. It can be ARM, it can be RISC. Since it's done by Intel, today it's actually x86 as well, right? Right? And this thing exactly gets the power first. So it sits somewhere over here on the motherboard, right? So we put the CPUs here, my cores, which we buy when we upgrade. But this PCH is given to the motherboard manufacturer by Intel. Intel has a very good agreement with them. They know what's going on, how to put this thing, but it's there. So that's yet another x86 core. Okay, and this thing is called management engine. So this thing actually gets the power before other CPUs. So this is the very thing on the platform which starts running. So memories are off. Those CPUs are still off as well. This thing is on. This is a very powerful thing, right? So this ring -3, I said. It's a full-featured core, which is called Intel Core. A couple of years ago, at least, that was the implementation. It's x86 Intel Core, 32-bit, right? It has its own internal memory, 1.7 megabytes, but it can also access the DRAM of the main machine through a DMA, Direct Memory Access Engine. And it can control the boot chain. Moreover, it can access the network interface on many of the motherboards. And it stays on most machines, even if you like, as long as the machine is powered, plug into this power outlet. So your desktop at home, you switched off the power, but this thing is still on. And it can send packets over the network, which is kind of amazing. You close your laptop, you said shut down, this management engine is still on. Has full control over your machine, can read any memory through a DMA agent. There is no address translation. You can just physically access the whole memory and can send packets over the network. It's a kind of a huge backdoor. That's why ring -2 or -3. It's always on, effectively. You have to unplug the battery and just make sure that you know that you really have to turn it off. You really have to try hard, right? The use case was to help enterprises to control those laptops. Imagine I am a high-up executive. Even if my power state S5, suspend 5 state, right? Computer is off. ME cannot access the DRAM because DRAM is off, right? Because we powered off, right? But it has its own memory, right? And it has a connection to a network. And if my laptop has a cell modem, I can remotely, if my laptop is stolen, send a kill signal. And since ME controls the boot chain, my machine will never boot again, right? So that's cute, but to a degree. So kind of, like this machine, anything what you have. I don't know what about, ARM has a similar technology, but I'm not an expert, but I don't know what happens on Mac OS laptops, but on any Intel laptop or server, that's the story essentially. Okay, Intel gave us a gift. So this thing is always sitting there. So if you really care about who owns your machine, so maybe the answer is Intel, right? But it gets a little bit even worse, right? Right. So, but huge opportunity of the attack. But let me tell you an anecdote first. So, people started looking into what's going on in that Intel management engine. Like security researchers, they make a fair amount of money, so it's a good profession if you're like inclined to do it. And they ask the question, okay, what's going on? Like, can we break in? And if I ask you a question, so what do you think is running on this Intel management engine? It turns out those people, most of the Intel management engine is heavily encrypted. So essentially it never leaves like this protected hardware in unencrypted form, but they left a couple of modules unencrypted. And if you search for strings in this unencrypted modules, so for example, you search for VFS here. VFS stands for Virtual File System. You will find a couple of matches, right, in those blobs of software which Intel management engine runs. And if you say, okay, I will put this on a Google search or some other search engine, I land on this search result, which means that FS bogus child for forking. This is exactly the line, FS bogus child for forking. What's this code base? Apparently, it's a code base of something what is called Minix 3. Minix 3 is it used to be Minix, which was a teaching operating system developed by a professor, Andrew Tenenbaum. He's now in Netherlands, right? So he teaches there. And here, then Minix 1 was like a goofy operating system, but he said, okay, I want to play the game of building operating systems. I'll build a better one, a microkernel one. And Minix 3 is kind of a capable microkernel. I wouldn't say it's super elegant or anything, but it's a microkernel and it runs, right? And that's the source code of his Minix 3 operating system, which is found inside this Intel management engine. So as a system designer, you say, okay, well, maybe the whole thing is Minix 3. Maybe they just took a part of the Minix 3 and said, okay, my virtual file system will be implemented by parts of Minix 3. We don't really know the answer, right? But at least it's running parts of this Minix 3 operating system. And if I ask you a question, is it exploitable? I mean, I know that you guys are not experts in exploitation, but what is your gut feeling? Yeah.
Everything can be explained.
Yeah, some things are harder, but we can take a look at this wonderful source code, which is our favorite C, right? Which says, okay, look, yeah, it's very easy to say, like, I will, like, do a buffer overflow here because I forgot the length of the array. So it's not a safe language, not Rust, nothing like that. So it's C. Like, if you start measuring the probability of finding a bug in the C code, in low-level C code, you will get a metric, like some number of bugs per million lines of code, maybe 1 per million in a well-tested code. Linux typically has like 250 vulnerabilities a year, right? So most likely it's exploitable, and it was exploited, right? So this is the company, they were breaking in, because this thing runs a web server, because, remote administration of your laptop obviously requires a web server, right? It's impossible to do without it. Like, of course, it's running there as well, and it was left unprotected and stuff like that. So anyway, so ME is a huge backdoor, and we all have it, right? And it turns out that Intel made it to run first, right? It starts first, this ME. ME reads the BIOS. So BIOS sits on this, remember I said read-only memory, which can be flashed, right? So it's just essentially instructions here, the program, probably the same L file, maybe beginnings of it can be a little bit simpler. So there's this SPI bus, and this gets read when the platform turns on, right? When you turn on the power. ME then essentially dedicates one of the processors, because you have a bunch of cores in the machine. And one of these processors is chosen to be a bootstrap processor. So it will do the job. All other processors are called application processors. They are just sitting idle, waiting for a special interrupt from this bootstrap CPU, right? And so at some point, this DSP starts reading parts of the BIOS as well, right? So after ME allows it to do that, ME also controls the microcode. Essentially, remember I said that x86 translates x86 instructions into simpler RISC instructions internally, and there's a piece of software which is running on the CPU itself. When you hit like a complicated instruction, it will be just implemented as a sequence of smaller instructions, and that's done with the microcode. But in the end, this bootstrap CPU starts reading the BIOS, and an interesting detail here, the DRAM is still not initialized. It's kind of off, and you need to start specific initialization code to make sure that you have DRAM, right? So you don't have DRAM, you don't even have caches yet initialized, right? So you can't really call functions, right? So because when you do a call, you have to push something, and there is no memory. There is no way to execute, to write something in memory. You can only read from this chip, right? So either you craft like a handwritten assembly, which doesn't do this, or there is even a compiler, which is called read-only memory C compiler. So it generates code from C that uses no stack, because there are some limitations. You don't always can compile anything, but you can compile some subset of C. And it's used in this core boot project. So this is just a bit of, again, interesting trivia here. Then they start, before even initializing the RAM, they initialize caches and then use caches as DRAM temporarily, right? And at some point, you copy the bits of this firmware from the chip, which was sitting here, into the DRAM. Like you initialize the DRAM and keep going on. Like that's a lot of happening, right? So what is BIOS? So BIOS, you can think of BIOS as a crappy version of an operating system. So sometimes it's full-featured. It even runs processes like multiple threads. The main point is to just make sure that the all peripheral devices are initialized correctly. And those peripheral devices sometimes require some initialization as well. So it's like essentially a network card today will run a tiny operating system on its own. And so BIOS will like talk and just execute this. It's called an option ROM. Execute, let it run for a while, stuff like that, right? So BIOS is tricky, right? But there is a huge fight today to make BIOSes more open, because it used to be that, it's a completely like closed environment. You don't know what's going on. It's again easily exploitable, and the reason it can either initialize your platform in some rogue manner, for example, loading a virus or a rootkit into the network card, and then from the network card you can attack the operating system, or load it even in memory and like do tricks like that. So essentially break the boot protocol, right? So again, but another interesting aspect is that Intel has a special execution mode, which I was calling ring -2. It's a protected region of physical memory. It's initialized once by the BIOS. BIOS loads something into that region, and this thing is always running. It's not always executing on the CPU because it will piggyback on the main core, but it periodically receives interrupts. And so it periodically can take over your machine, right? And run something, scan your memory. So remember, you have those horror stories about your supervisors snapshotting your screen while you're on your work laptop. So this is done with this system management mode. They just load. They have like those companies which develop motherboards and provide chip BIOSes, like, I don't know, let's not use the names, but they will provide some piece of software which provides a way to do this remote administration. Sometimes it's useful, your laptop doesn't boot because you screwed up operating system. They will just boot into this system management mode and maybe reflash the whole laptop, right? But you see, like sometimes you can click some button, say the recovery mode. That's what essentially some interplay with that. But some scarier things can be hiding in that system management mode. Like again, whoever started this mode controls the machine, right? And again, the beauty of it is it's the same plain C, so it's exploitable. If you're clever enough, find a bug in the system management mode, you can own this machine for quite a bit of time. So it's hard to, your antivirus tools will not scan the system management mode. It's hard, if not impossible, right? So yeah, ring -2. So it's also running there, right? Hard to disable, not impossible, but hard, right? And then finally, this BIOS, on the end of it, we finally got to the point when we jump to the boot block, right? So as we say, BIOS can be quite sophisticated, since it can be full-featured operating system. If you say, I want to boot from a network, it will have a TCP stack and will connect to a network and will read the operating system from the network, right? You've seen it. It can boot from a USB stick because it understands USB protocol, right? But in most cases, and especially in legacy machines, what happens is the following. That was the kind of the mainstream protocol, right? Like you can load it from anywhere, but default way is to load the first sector of a hard drive, right? It will only load 512 bytes. So if you have a disk, which is like disk number 1, let's say, and it has block of 512 bytes, block number 0, this is what BIOS will load by default. So this is where the bootloader, or essentially the very first part of it, will sit. Just because maybe your bootloader is also so sophisticated that it will go over the network. But in order to go over the network, you need a network protocol, so it's unlikely that you will be able to fit it in 512 bytes, right? So it's only 512 bytes, right? This is what is read from memory into the memory location 7C00. And this is where the BIOS, when it says, okay, I'm done running, I'm done initializing my system management mode, and I will never let you know what's inside there, it will configure instruction pointer IP register to this address and just starts executing. So whatever your boot block contains, it got loaded by the BIOS into this 7C00, will start running, right? This is how we get to the bootloader. And the bootloader will load the operating system. So we'll spend the second half of today, or maybe part of it, explaining how we're going to boot, right? So, but this is how we get here. And when you will configure the QEMU virtual machine, it will do the same. It will also execute the BIOS and will essentially load the boot block from an emulated disk device. And this boot block, we will essentially write it. That's your homework assignment. You will start writing this bootloader essentially to boot into Hello World, right? So it will do the same. So let me stop here for questions. Okay, anything?
Just to clarify the BIOS, you actually boot the OS as well.
Right. So, and the way it's done, that it cuts out the region of physical memory and hides it from the rest of the system. Even the operating system cannot access it. And it puts some software in that region. And normally it's not running, it's sitting idle. But once in a while, there's a special interrupt or a collection of those interrupts, which transfer control, essentially saying this interrupt is not received by the operating system, but it transfers you into that special mode of execution in which this system management mode is running. So it's in control, like once every so often, like there is a timer or terminal interrupt which triggers it. Right. This is the because there is no other CPU, so it will run on that CPU, on the main CPU. It will use your caches, pollute them, and this is how you can measure that it's actually present. And this is why it's also painful for people who imagine you do high-frequency trading, essentially, and once in a while this thing kicks in and your transaction fails just because there is like micro or like tens of or hundreds of microsecond latency. Something was going on. You say the machine wasn't mine at this point, and you lost so much money that those people are also kind of paranoid and they try to disable it. So, or like real time. Imagine you're driving a car and suddenly you have to react. So 10 milliseconds is a long period of time, and this thing just like froze the machine or froze the core, and you hit somewhere. Not a pleasant thing. Yeah. Anything else? Any other questions? Oh, I can't hear, but maybe. Talk about a little bit about UEFI. No. It will take us. It's just a kind of like a BIOS or a boot standard. So I'm not an expert. It will take us forever. I can dig it up for you, but this is like the modern standard essentially.
Does the BIOS only load the first 512 bytes? And that first 512 bytes just loading the rest usually?
Yeah. Right. Yeah. Typically, and this is what we will see. Like we'll take a look at the actual code, which loads the rest of the kernel from disk. Like in our case, we will just be using a one-stage bootloader. So just this 512 will immediately go to disk and load the kernel into memory. If you're running something like grub on Linux or some fancy loader on Windows, I forgot the name for it, this 512 bytes load the second part of the loader in memory and start executing the loader, like grub, for example. That's why you see the menu. Grub is like an operating system on its own, small one, but it understands like file system layouts, NTFS, ext3, stuff like that, can go over the network to boot from the network, right? So it's a lot of code running. And then eventually you choose how to boot, grub will load the kernel in memory and kind of say, okay, I'm done. And that memory can be reused. But typically bootloaders are two-stage, but we will use only one stage. Anything else? Okay, so let's dive. That's my diagram, kind of. I simplified here. I erased all this system management mode. There is no memory engine, management engine, right? So just core. Let's imagine all the segment registers are zeros. GDT is 0. IDT, interrupt descriptor table, is 0. Instruction pointer points to 7C00. Segmentation and paging are not yet even enabled. So we only use physical addresses. And the mode of execution is actually 16 bits. We're not even running in the 32-bit mode, right? This is how all the stages which were running before us, and BIOS was running, and they just reset everything back to this, right? Just to make sure that we can boot the legacy operating system. So that's why UEFI essentially cuts some of those steps, and the boot is a little different. Okay, so essentially, this is essentially the boot block from the x86 operating system, right? So here I show you the path within the x86 source code. It's a file which is called bootasm.s, right? I will keep showing files for a while so we know where we are in the source code. But this is essentially what you can control as a student in this class. So you can just essentially, let's erase this instruction and see what happens. Well, you can recompile and boot it. And x86 boots on real hardware with a little bit of fixing, right? But we will boot it under QEML, right? But anyway, so this is the code. So start label. This is where the boot block is compiled to start here, right? So we're going to link it to start from this instruction. The very first instruction is CLI disables the interrupts, because maybe BIOS was talking to network cards, disks, stuff like that. If they send us an interrupt and our interrupt descriptor table is not configured, then we're going to crash, right? So that's why we disable the interrupts right away. Then we don't really even know the state of the segment registers. Maybe they are not zeros because BIOS was using them. Maybe not. But just for the sanity of it, just let's just set them to 0. So we use a XOR instruction which produces a 0 in the EAX register, and move the, like I'm using AT&T syntax here, moving this 0 into the data segment, the extra segment, and stack segment, right? So just to make sure that everything is 0, right? It's kind of natural, nothing super special happening here. If I ask you, since we know that we have to start at 7C00, right? So we need to compile this code in such a manner, or link this code in such a manner that the start label is exactly at 7C00. I kind of was talking about this tooling, right? But let's just take a look again. So we have to be careful because otherwise the code will not run, right? So this is the part of the make file, which, and we kind of mentioned it before. So which compiles, which process this boot block target, right? And essentially what it says here, so we take this bootasm.c and a C file, bootmain.c, will produce a couple of object files, which will be bootasm.o and bootmain.o. Those are the L files, are good old buddies. We know what's inside them, right? But we will tell the linker to say, the entry point, please take the start label as an entry point and compile it at 7C00, right? In the homework assignment, I said, okay, link it. Sorry, not compile, link. I said link at 0, but I can also say link at 7C00, right? This is where we want this code to be, because we know that this code will be placed there by the BIOS, and so if we want the C variables to be resolved correctly, there's no position independent code here, nothing, right? It's like just statically linked. We have to make sure that if you have a global variable, it has to be somewhere in 7C0, I don't know, F, for example, right? So that's why this is important. And remember, we talked about it, and there's this Perl script, and someone was asking me, okay, what is it going on here? What is this Perl script checking? This Perl script actually checking that the final boot block is less than 512 bytes, because it's overflows, and I was playing with x86 doing something funky with it, and at some point my boot block started overflowing. Essentially, it got larger than 512, and this Perl script stopped me. Otherwise, I would crash in some unpredictable manner, right? Because half of my program would not be loaded. Only 512 bytes are loaded, right? Okay, so this is, again, this was x86 make file. So if you want to read this, and those are the actual lines, right? So remember, I said that x86 comes with a printout, and it changes from year to year, but I think the numbers haven't changed, right? So I actually copied from this PDF. So if you care to find this line, you can either go to the source code, to this bootasm.s file, or you can just take a look at the PDF printout, and this is the line in the PDF. Sometimes I might make a mistake, and the line might differ, but in most cases, it's correct, right? Okay, cool. So our goal now, we want to switch from 16-bit mode to 32-bit mode. For that, we need to enable segmentation, right? Remember, segmentation uses this global descriptor table, right? There is a special instruction, load global descriptor table, and this is the address of this global descriptor table, right? Where is it? So my GDT can be very, very simple, but it has to be part of the data section, essentially, in this boot block, right? So this yellow part, my GDT, again, this is why I was teaching you segmentation, just to make sure that you guys understand that it's there, right? So it's sitting there, right? So this is a specific address which pops up on my machine when I run my version, and this is my instruction pointer. Those are zeros because we just essentially put them to zeros, right? That's again just a recap, but we just did it so we know, right? I just wanted to understand that we understand the translation, right? So if you're coding in assembly, this is how you define this global descriptor table, right? So this GDT descriptor, and it's defined by the CPU. It says, okay, there will be a word which essentially says it's a size of the GDT, and then the GDT pointer itself, right? So it's like two things, right? So it's like a struct in C, right? But you do that in assembly, right? And so you say, look, I will force a 4-byte alignment here. I will define the GDT. My first entry, we use a little bit of matrices here. First entry is never used, so it's like you just put zeros there. And then you configure two entries with this macro, because the format of the descriptor itself, the bits are shifted like that, like somehow some permutation is happening for historical reasons, for backward compatibility, so it's easier to write it. So you say, I will define two entries, one for the code, one for the data. So this will be used by the CS segment, and this will be used by DS and stack segments, right? And you say start address for both of them will be 0, and the limit will be all Fs. We'll cover the entire address space. We don't have to say, like, forget about segmentation. We just want 0 added to all the addresses. One of them will be executable and read-only, and the data segment will be writable, right? Bits of assembly. Just wanted to explain it, because if you read the source code and you will be coding it in your homework assignment, just make sure that you're not confused about what's going on, right? And since you say, I want to provide an address of the GDT, so what you do is that you say, I will subtract the address of this label from this label. I will subtract this label, right? And then -1. So it's size of this thing -1. That's what the standard wants it. And that's the pointer. That's an address of the GDT label, right? Okay, let me stop here, and we'll continue booting. So essentially, we'll see how this GDT is used and how we'll get to essentially load the kernel. So it will happen on Thursday. Say again?